In this video, I would like to give motivation for complex numbers and to define them. So, why complex numbers? For example, if you try to solve the following equation, x squared plus 1 equal to 0, you would quickly find that x is equal to plus and minus square root of minus 1. Until the introduction of complex numbers, we would say that this equation just does not have a solution. However, with complex numbers, we can say that x is equal to plus or minus I, where I is the imaginary number. So you can see that the imaginary number is defined as the square root of minus 1. Using imaginary number in combination with the real numbers, we would quickly find that now we can solve any polynomial over real numbers. For example, we can now solve the following equation, which we were not able to solve before. Using the quadratic formula, we will find that x is equal to minus 1/2 plus or minus I square root of 3 divided by 2. In this case, x is a complex number. We refer to the first part as the real part and to the second part as the imaginary part. So we have that real part of x is equal to minus 1/2 and the imaginary part of x is equal to plus or minus 3/2. Alternatively, we can write x as an ordered pair, where the first number is the real part and the second number is the imaginary part. You can define the complex numbers as a combination of real numbers and imaginary number. Complex numbers are usually denoted by C, and they're usually written as z is equal to xy equal to x plus iy, where x and y belong to the real numbers. Note that real numbers are a subset of the complex numbers, since for all x that belong to the real numbers, x plus I times 0 belongs to complex numbers. If we were to square the imaginary number, we would have square root of minus 1 to power of 2, which turns out is just equal to minus 1. Using this relation, we can derive product for complex numbers. If we had z1 multiplied by z2, we know that writing in coordinate pairs, we have z1 is equal to x1, y1, and z2 is equal to x2, y2. Rewriting them using the imaginary number, we have x1 plus I times y1, all multiplied by x2 plus I times y2. Multiplying everything out, we get x1 x2 plus I x1 y2 plus I y1 x2 plus I squared y1 y2. Note that y squared is just minus 1. So we can rewrite this as x1 x2 plus I x1 y2 plus I y1 x2 minus y1 y2. Grouping real and imaginary parts together, we get x1 x2 minus y1 y2 plus I x1 y2 plus y1 x2. Rewriting it as the coordinate pairs, we get x1 x2 minus y1 y2 x1 y2 plus y1 x2. And this is the product relation for the complex numbers. To find the sum is much simpler. Sum is just given by z1 plus z2 is equal to x1 y1 plus x2 y2, which can be rewriting it using the imaginary number. We get x1 plus y1 plus x2 plus y2. Rearranging terms and grouping them, we get x1 plus x2 plus y1 plus y2. So we have that the sum of two imaginary numbers is still quite straightforward, unlike the product.